So there's been a lot of discussion about the sustainability of the school, of the middle school, and it's one of the tenets that we're building a new school on. And I know folks out in the community may have heard of Energy Star, the U.S. Green Building Council, which is the leadership in energy and environmental design. The petals you see there on the right is the Living Building Challenge. I don't know if people are familiar with that. There's the New Buildings Institute, the Well Building Institute, Green Globes, CHIPS, which is well, they used to be the California High Performance Schools, but now it's the collaborative for high performance schools, because now it's nationwide, and then Passive House. And all of these are rating systems, third-party rating systems that we can follow putting the school together. Many times we look at the measures and the strategies from all of these programs to choose which ones best fit the school that we're working on. Tonight's conversation is going to be more about energy consumption than site development, water conservation, indoor air quality, and materials and resources. But we don't want to make the mistake to say that we're not concentrating on all of these things. And every single one of those programs that we just talked about on the slide before, that's their main focus, are these 5 attributes of sustainability. We look at sustainability as really a return on investment. So what you see here is we're going to work very hard to balance the upfront cost of how much are we putting into the school in order to recognize savings over time. Because we believe that a sustainable school is just that. It doesn't cost you an arm and a leg, it sustains itself over 50, 60 years. So with that, any questions about that piece? Because I'll go right into the net zero energy discussion. So one thing we're trying to do is reduce the amount of energy that the school uses every year. So there are numerous definitions of net zero buildings out in the world. You may have heard the term net zero building. The Department of Energy, the U.S. Green Building Council, they all define it as essentially your building is going to generate on site as much energy as it uses from a source. So what that means is, you get delivery charges and so forth. Whatever it takes to get to the building, you're going to generate that much energy. There are other definitions, such as the New Building Institute, the International Living Future Institute. They know the difficulties of dealing with a source, because your source of energy may be a coal-fired electric plant, it may be hydroelectric, it may be nuclear. So they're more interested in what it does on the site. So their definition of a net zero building is that 100% of the building's energy use every year is renewed on the site. So if you use a cup of energy, you're creating a cup of energy, and that's what gets you to net zero. If you create 2 cups of energy, then you're net positive. The other piece of that is the New Building Institute and the International Living Future Institute also would classify a net zero building as having zero combustion on site, so no fossil fuels. And that gets into net carbon, and we'll get into that in a second. Because their definitions and other definitions of net zero have to do with the top one that you see there, which is called net zero site energy, which is the definition we just talked about, which is however much energy we use on this site, we'd like to produce exactly that same amount of energy. Then you may hear source energy, and like we just talked about, if you're using so much oil or so much coal to generate that power to get to your building, you have to offset that as well, and that's extremely difficult to do. Then you may hear terms like net zero energy costs, which means you don't pay anything for electricity. Or for fuel, or for any of your energy. And that also is very difficult. You can imagine when you get your electric bills at home, you're not only paying for the electricity, but you're also paying for delivery charges. So even if you offset the amount of energy coming to the school, you still have to pay that delivery charge, if that makes sense. And then there's net zero emissions. And that, again, is the idea that if you have have fossil fuels on site, or if you're getting it from a source that you're balancing out and you're trying to get to carbon neutral. Another very difficult thing to do. So for our project, we'd like to define this as net zero site energy. So whatever we produce on site is going to offset what the site consumes every year. And that's the goal. And it is a very aggressive goal, but we can walk through what that means. There are certain milestones. I just wanted to let everybody know that people really started talking about net zero projects in their community as far back as 2002. LEED, which is the U.S. Green Building Council's protocol for sustainability, that started up as a pilot program in 1999, and soon thereafter people were saying, well, why are we shooting for 35% better than code? Why don't we get to net zero? NBI has been tracking this since 2010, specifically net zero buildings. NBI has been tracking building performance in their high performance buildings for 30 years. The International Living Future Institute, same thing, around that same time, 2010, 2011. So what you see here, in short, is that there are many organizations that actually track net zero buildings because they take it seriously. And they want to make sure that when people do say, hey, we have a net zero building, that they actually do have a net zero building. So just to demonstrate how difficult it is. So basically for K-12 schools, which is what we're doing, there's one private K-12 school which has been certified as a net zero building. It's not a public school, and I believe it might be in Connecticut. I don't really know where that one is. And then there's verified. Verified means that they take 3 years of operational costs and they actually prove that you're net zero. There are 0 K-12 private schools and 0 K-12 public schools in the U.S. that have done that. Emerging schools means they're registering with the intent of being net zero. There are actually 2 public schools in New England. They're both in Cambridge, Massachusetts. Cambridge has a very aggressive zero energy program in their city, and it's the Martin Luther King School and the King Open School, both in Cambridge. But there are also 5 others, so 4 other private K-12 schools have joined the one up at the top. And what that means is they're continuing, even though the buildings are done, they're continuing to go back into those buildings to try to reduce the loads of the energy that they're using, or they're actually adding renewable energy systems to the site, such as photovoltaics. So it's a challenge, and we're always up for a challenge. So this is what we're talking about. So how we do that is we make sure that the entire team, and that includes the owner and the architects and all of the engineers, consultants, are looking at energy use intensity targets. So the energy use intensity is called an EUI, and you can actually figure out every single building that's out there what their energy use intensity is. And what that means is you take all of the energy, whether it's from oil, propane on site, natural gas on site, electricity on site, you translate all of that to kilobtu's per square foot per year. So you add up all the energy it takes, you divide it by the 12 months, and you divide it by the square foot of the building, and that's going to give you an EUI. What we're targeting is an EUI of 25. And just to let you know how aggressive that is, what you see there is it says that in climate zones 1 through 4, 1 being the most mild, I believe 7 or 8 is the most extreme, like in Alaska. We're in climate zone 5. So the average EUI for a net zero verified school is 22 in climate zones 1 through 4. We're going to use more energy because we use more heat because we're in climate zone 5. The New Building Institute says that the average emerging net zero school in climates 1 through 4 is actually 35. So, and that's important because we're going to see an example in a few minutes of a school that is pretty much 35 and has no renewable energy on site. Codes and standards, we've talked to the building inspector, we've talked to the town of Durham, and what we're shooting for is all of those standards we talked about at the beginning. We look at all those strategies and measures, and we try to employ as many as we can in the building, but we will comply with the International Energy Conservation Code 2018. We believe Durham is either in the process of adopting that or will adopt that by the time the building starts construction. We also pay attention to ASHRAE 90.1. ASHRAE is an organization that essentially has targets for energy use throughout a building. All of those protocols that we talked about earlier use ASHRAE as a benchmark. And then there's the Chapter 7 of ASHRAE 189.1. So the reason why that's important is ASHRAE 189.1 is a green building code, although it's not a code, it's a standard, I should say standard. But Chapter 7 deals with return on investment. So in other words, ASHRAE is basically saying best practices is you should put in any new building renewable energy systems that pay for themselves in 10 years. So they understand that if something's going to pay for itself in 20 or 30 years, you know, maybe it doesn't get employed into the project. But if it's going to pay for itself 10 years, you should go ahead and do that. And all of these things will be put together in what's called an owner's project requirements. So when we get together with everybody at the building committee level, we're going to talk about what do we want to do, what are our targets. And we're suggesting that one target be that EUI of 25. Just as an example for the collaboration across the disciplines, if we were putting in a standard hot water heater in the building for domestic hot water, and it took 9 million BTUs per year to operate that hot water system, we would take a look at how do we define that in terms of net zero, what we want to deal with it at the site. Are we using fossil fuels or not? So what that means is the hot water heater electric or natural gas, propane, so forth, and you'll see in a minute why that matters. We would do a life cycle cost analysis to find out the best piece of equipment to heat that water. We'd look at thermal storage and how we can use that in multiple ways throughout the building. Then what are your expectations for that domestic hot water? Can we use a solar hot water array, which is something we employ on many of our projects? What that does is it uses the sun to pre-treat the water before it goes through your hot water system. And then there are solar arrays, which are, the PV stands for photovoltaics. That's taking sunlight and basically turning it into electricity. So if you had an electric hot water heater. So again, this is an example using 9 million BTUs of heat annually for the domestic hot water. And the reason why that's important is because if you did an electric heat pump to heat that hot water, you would be buying 3 million BTUs of electricity, which would actually generate 9 million BTUs of energy, because the heat pumps are so efficient at 300%, I should say, of the energy that you're buying, as opposed to something like natural gas. If we were using a boiler with a fuel fire that has a factor of 0.9 instead of a 3, you'd be buying 10 million BTUs in order to get 9 million BTUs of energy. So how that calculates out is if we were looking at doing solar panels to offset the energy for just this one piece of equipment, we would be using 3 million BTUs, or trying to get to 3 million BTUs, so the required photovoltaic array, solar panels, would equal that same 3 million BTUs. Because from the 3 million BTUs, we're generating the 9 million. The second option is if we had natural gas, which you have here on site right now, if we were doing that and we're trying to get the 9 million BTUs, we're not generating 3 million BTUs, we have to generate 10 million BTUs, which means your photovoltaic array is more than 3 times the size of what we would need to offset the electricity. I don't know if any of that makes sense, but it's basically saying that, you know, electric, the easiest way, if you want to call it easy, to get to a net zero building is have an all-electric building. And the New Building Institute recognizes that, and so does the Living Institute, which is why they say no fossil fuels on site. But that has a big money impact. For anybody in the community, you pay a lot less for natural gas than you pay for electricity. So that's why getting to net zero money is a whole different story. So how we do this is we leverage energy modeling throughout the entire process. In fact, we're doing energy models right now, and we really have just a concept design in terms of the building. But what we're trying to do is find out if the building is shaped and oriented on the site as properly as it can be, to harvest as much daylighting as we can, because the goal here is to use this energy model to drive down the energy use in the building before we even talk about what kind of systems are we going to have to actually provide the energy for the building. Considerations of size. So this is just a very quick analysis of the site that we did. If our building is roughly 145,000 square feet and we're shooting for an EUI of 25, all of this calculation essentially means that if we did an all-electric building, we would need roughly 60,000 square feet of photovoltaics on site. So if you look at the site plan like we have right now, which we'll look at in a minute, we can look at it right now. Between the roof of the building, the parking lot, so there's two pink areas up at the top of that slide that say parking. If we were to put a canopy of solar panels above that parking, and we had solar panels on the roof, we would have roughly 80,000 square feet of surface area to put in the solar panels that we're talking about. You would need at least 60 to get to where we need to go if we had an all-electric building. If we have a combination of electricity and fossil fuels, like we showed in a few slides ago, if you're using natural gas, you need a lot more solar panels to offset that amount of energy. So moving on, there are incentives. New Hampshire Public Utilities Commission does give what they call renewable energy credits, and they give those credits for customers such as yourself who put in photovoltaics and geothermal systems. So there is some benefit to doing renewable energies. It's not a big deal, but there is money available. You have to apply for it, you have to get selected for it, and we will be doing that. The other thing that we're doing in terms of strategies and measures is we've already talked about making the building as compact as we can, which actually works very well with the program that we have for the middle school, which is team teaching. We've talked about a 4-story building. So what we're doing is we're getting the maximum amount of space with the least amount of exterior envelope. So a square is typically your most efficient shape. And the exterior envelope is the most expensive system to put on a building because that's where all your wall insulation is and your glass, your insulated glass. And so by reducing that, you have obviously less loss, energy loss through the walls, and it also has a roof over it, so we're actually trying to condense the roof as well. And some of those things, just to quickly go through, what we try to do is strategically use windows to walls. Excuse me. The wall of a building, if you insulate it properly, is your best insulation. And that's where your biggest bang for your buck is to properly insulate a building. So we try to only use 25%, 30% at the absolute max, of glass on a building. That 25 to 30%, if strategically used, number one, in a school, makes it very welcoming. But it also takes advantage of enough daylight harvesting so we get daylight into as many spaces as we can, which allows us to shut the lights off. Knowing that we're going to most likely use all LED lights in this building, the energy use for the lights is a lot less than it used to be when we were using T8s and T5s and things like that. So our goal is to try to get daylighting into 90% of regularly occupied spaces. So what that means is the classrooms. We're looking at double pane and triple pane fiberglass windows, and that gets us an R value of between 7 and 10. Cornier is a curtain wall and storefront manufacturer that makes ultra-thermal frames, which has an R value of just over 4. which is actually a lot better than normal frames. And so that's what we'd be looking at. On the roof, again, the roof and the walls are the most important thing. So we put down a base of 6 inches of insulation, and then anything that tapers up from there is more. So we're looking for an average of R40 across the entire roof, or R45, I should say. The exterior walls, even though they're metal studs like you see in commercial construction, we look to use 4 inches of polyiso on the outside of the wall and 3 inches of foam in the cavities to get to a minimum R36. These numbers that you see here are basically prescriptive measures put out by the New Building Institute, who've been analyzing buildings for 30 years. Some of these numbers are a little bit more than what they would recommend as a minimum. And we also couple this with Passive House, who is, one of their big things is insulation. And so we take a look at what Passive House would recommend as well. We would then have 4 inches of continuous insulation under the slab. So the earth is roughly 50 degrees, if you use that as a rule of thumb, so it's always sucking energy out of your building through the slab of a building. So we actually put 4 inches of insulation below that slab. And then we use 2 inches of thermal break around the perimeter of the building so that you don't get heat loss around that slab at the perimeter of the building. And then buildings are only as good as you operate them and as good as they're set up. So we recommend commissioning. Traditional commissioning takes place during construction. We recommend to get the commissioning agent on board during design, so they're actually looking at the systems that we're designing so they can talk about maintenance and operation and the controls of those systems. And then once you're in the building and everything's calibrated and running great, we would recommend that they come back a year after operation, take a look at everything that's doing, go back and make all the adjustments. And this has proven to be money worth its, or I should say, worth its weight in gold when they come back, because what happens is you hand the building over and there's a learning curve for the maintenance staff. We do all the training for them, but at the same time having them come in and see how this building is being used. In other words, what are the teachers doing, what are the staff doing, what are the kids doing in the building? Commissioning agents can actually readjust and calibrate the equipment differently based on the actual usage that's going on. So it gives people a year basically to flush out the building. So just some quick tidbits of information. We've analyzed your existing school. We've taken a look at all of the money that you spent in 2018, and we took a look at all the energy use that you used in 2018. So you're operating right now at an EUI of 50.22. So that 50.22 though is a little skewed, and the reason it's skewed is you don't have central air conditioning in the building, and you don't have code compliant outdoor air ventilation. So there is some ventilation obviously in the school, and the windows are operable. I suspect they don't open in the wintertime though. And so between the ventilation and the air conditioning, you're able to recognize some savings over what a new building would provide. And the other thing that you have going for you is natural gas. So you're paying for natural gas instead of electricity, and the natural gas is your primary source of energy. Even though you have electricity in the building, most energy you're buying is through natural gas because it's a heating dominant building. And so you're only paying 90 cents per square foot right now. If we factored in what we believe it would cost you if you had a central air system and if you actually were ventilating the school to be code compliant, you'd be around $1.15 per square foot. We checked all this with Jim, by the way. He gave us all this information. So then predicting the new school, if we were targeting an EUI of 25 and we were able to get the renewable energy credits that we're talking about, you'd be able to pay 94 cents per square foot instead of $1.15 per square foot. So what that means is that if we added a minimum of 40,000 square feet, so our new building is going to be about 40,000 square feet larger than your existing building. We know that if we did an addition renovation, it wouldn't be 40,000 square feet. It'd probably be more like 50 or 60 because of the inefficiencies of the existing building. But I just wanted to say if we added 40, over the next 20 years, it would cost you $3.4 million to operate the building. and the new school over 20 years will cost you around $2.7 million. So there is some savings there, although it's not a lot because you pay a lot more for electricity than you do natural gas. And our recommendation would be, if you do have fossil fuels, they're on site for backup, not for your primary source of energy. And this is Energy Star. The Department of Energy has a program called Energy Star Rating. And if you plug in all of the numbers, for instance, your electric bills and your gas bills and things like that, it'll spit out what your EUI is. And when Jim did this, it came out as a 51. So we think, when we crunched our numbers, we think you're doing a little bit better, but this is just a boilerplate thing on the Energy Star website. So just as an example, this is Wells High School that we did a few years ago. Wells High School is in the same climate zone 5. It's actually not that far from here, Wells, Maine. And that building was designed, it was the first Maine advanced building for a public school in Maine. This was designed to have a geothermal system and a photovoltaic system, but neither one of them were installed. So what they have here is just a well-insulated, well-ventilated, all those things that I just talked about, without any geothermal system and without any solar panels. And the New England Energy Efficiency Partnership highlighted this school with 2 other Massachusetts schools as the 3 exemplar schools last year because this is operating with an EUI of 37. So, and again, they also have operable windows, but they're pretty diligent in how they operate the building. It was commissioned. So this is just an example that if you do the building even without renewable energy systems, you can do, if you do it right, it can still operate as a very energy efficient building. Strategies and measures, we believe that the building is a holistic approach. So every time we have daylighting, we have less insulation in the walls, but the daylighting actually enhances the educational environment exponentially, but it also reduces the use for artificial lights. If we have heating and cooling within the building, again, educationally, it makes a world of difference. And it also keeps a very healthy building. You'll notice that the International Well Institute was one of the programs that we talk about, because it's very important that as we're doing this, we're creating a building that supports wellness for all the students and for all the users of the building. So we talked a little bit about putting solar panels above parking lots. This is a high school in Massachusetts, and you see there in the background, the parking lot is covered with solar panels on stilts, if you will, columns. This is what it looks like up close. So you can see that you just basically put this over all the parking areas. The one thing that it does is it covers up all your asphalt. So you don't have as much of a heat island effect, although the solar panels are black, so they still give off heat. And this is another one, this is at UMass, and in this one you can see that the solar panels are pretty far away from each other. But at UMass, they're very close to one another. The ground's all wet because the pavement pitches in that direction. So when the uncovered portion of the parking lot, all the water runs across it. But what we were talking about was being able to park the buses, school buses, underneath a canopy like this so that you don't have to pay for all the snow removal and such. The inverters for all of this are right out on the columns that support this. It's an educational opportunity for all the students in the community to see how all these things work, how much energy they're generating. We also talked about future readying the building by putting in electric charging stations in the parking lot, and especially in the bus parking lot, in the event that the school ends up with electric buses 10 years from now or more. And then this is what solar panels look like up on a roof. They're all connected. We do leave a little bit of space between each one so we can still walk around on the roof. And there are power purchase agreements that enable you to look at funding a different way to get these solar panels up on the roof. And then, the geothermal system has been a topic of discussion since we started. And there are really 2 types of systems. And I just wanted to let everybody know, we're suggesting a closed loop system, which means we're not dependent on groundwater, we're not touching the groundwater, we don't care if there's groundwater in the rock or how deep it is. What we really want to do is use the earth itself as a heat sink. And so basically we just talked about the earth being 50 degrees. So what we want to do is run water and refrigerant through loops that go into the ground and come back out of the ground. And all it is just water circulating through the earth. And what that's doing is that's actually heating and cooling your building. So there's nothing to do with groundwater. This is basically what it looks like for a traditional building. They're called boreholes. In fact, they don't even call them wells anymore because it's so confusing. When people think of a well, they think water. So they're called boreholes. The nice thing is you got a lot of rock out there, and the best site to have boreholes on is ledge, is rock. Typically, they're about 450 feet deep. So the loop would go down 450 feet and then come back up. This is a project right now that I'm working on that they just completed the well field. There's 112 wells on this particular project, and that's essentially what you would have, and we're thinking about putting these underneath your parking lot. So they drill the borehole 450 feet deep. There are two black polyethylene pipes coming out of those boreholes, one's supply and one's return. It's like one big loop. There it is in the other direction. Then what you do is connect all the wells together, right? So you have this horizontal piping that goes across. So you're picking up all of these boreholes on a circuit of water. That's just another picture of it there. And that's actually the borehole itself. So you can see it's either 8 or 10 inches in diameter. They drill it down into the rock. They fill it with grout, and it's a special kind of grout that allows the conductivity of the earth to get to the pipes. And that's pretty much it. So it's a very simple construction. We've put these under ball fields and we've put them under parking lots. So the next steps is to continue talking about these things, to have a technical review of the building itself and talk about the envelope, which is the walls and the roof, building orientation, whether there's operable windows or fixed windows in the building, take a look at the controls of the building, and take a look at managing the loads, the energy loads of the building, and then actually select systems for your solar hot water, your kitchen equipment, heating and cooling, and then any kind of backup systems that you might want. And that's it. Yep.
Thank you. I have two questions. I should probably talk. The first question I have is, I'm not quite understanding. I mean, I understand that electric is more expensive, say, than natural gas. I get that. But if we are also utilizing these solar panels and the geothermal, I guess we're not really going to be paying as much for electricity. I'm just trying to understand that whole concept.
Right. So I think in one of the slides we said that if we, based on the size of our building, we'd be looking at 818, some number like that, of a kilowatt system. Okay. And that's what's taking up the 60,000 square feet. So if we're generating as much electricity as we're using in the building, it doesn't all get generated at the same time. Mm-hmm. So you're going to still be paying for delivery charges from your utility. You will not be paying as much for the electricity itself if you buy these things outright. So we have a client right now who looked at a power purchase agreement, which is something that allows a school to put the solar panels on the building at no upfront cost, zero.
Oh, okay.
And essentially you then lease, or I should say the power purchase agency, the agency that puts the solar panels on your roof, they lease your roof space.
Okay.
And you pay them for the electricity. So they work out, they look at what you pay so that basically you're not paying any more. Mm-hmm. You may actually be paying just a little bit less, okay, but you're basically paying the same amount
Okay.
to generate that electricity, but what you're getting is less electricity coming from the grid.
Yep.
So that's where you're either paying a power purchase agreement or you're paying for electricity.
Okay.
So that's why the money's not zero.
Got it.
We do have a client who decided they're not going to do that. They're going to spend, several hundred thousand, well, I think it's between $400,000 and $500,000 and buy the solar panels outright. And the reason they're doing that is exactly your point. So for the next 20 years, they're not paying for a power purchase
Got it.
lease,
Okay.
and they're not paying for electricity for the amount that they make.
Got it.
So that's the,
Okay. And then my second question, and I apologize for just not knowing this, but if you have all these solar panels on the roof, if you have like a huge snowstorm, is that a concern that there's all the weight of the snow? And I mean, I understand that the solar panels are, obviously the heat and all, but if you have a really big snowstorm, is that a concern?
right. No, I mean, you'll have a few days where they're not actually generating electricity. It's the UV rays that actually get to the solar panels that move the electrons that create the electricity. So depending on how thick that snow is, the UV rays can still get there, but they will melt quickly. But they're not going to generate as much electricity until that snow does melt.
But it's, the weight of it isn't a concern
Oh,
on the solar
no.
panels?
So the
or
roof,
anything like that?
the roof and the structural systems will all be designed, and really, it's not even snow that we're worried about anymore. It's this freezing rain
Freezing rain, right.
that ends up, soaking the snow, and basically what you've got is buckets of water
Right.
on your roof and not the snow. So,
Okay.
but yeah, the weight won't be an issue.
Can I just follow up on Denise's question, Ron? Because 3 years ago, we did have to spend quite a lot of money removing snow from the roof because the storms were so heavy. Are you saying in the design of the new school, we wouldn't have to be concerned with the weight of snow on this roof?
Right. Yep. Yeah, because engineers, like even as recently as 5 years ago, and I think the codes are catching up with it, but engineers were realizing that that's, you can do a code compliant building or you can do one to reality. And the ice storms and the rain we get, the worst thing, if you want to call it worse, is when you get a lot of snow and then it warms up and it rains and it really saturates that snow.
Right.
That's where you do have to get up there and start getting the snow off the roof, because you're no longer looking at a snow load, you're looking at a slush load.
Right.
And there's no code written around slush right now.
So if that were the case, if we were there this year and the school was up, how, with the solar panels on the roof, how do we remove the slush?
It would melt away.
We
because-
wouldn't have to physically go up there and move
No.
it like we are now.
No, I mean, you could if you wanted to, but you wouldn't have to go up there. Obviously snow, I've actually seen snow blowers up on the roof, which, but I don't think you'd need to do anything.
Okay.
No, it would melt away. Because you're certainly not going to get up on those car canopies.
Well, that's what we're asking.
Yeah.
Rod, just something we've talked about in our meetings. Your conception of this building would be that it wouldn't have windows that would open and shut. Is that correct?
So, yeah, we've done a couple of projects now where the owners decided that you've got a fully heated, fully air-conditioned, fully ventilated building, all being done with energy-efficient systems, so there's really no need to open a window. And I've walked by some schools that we've done, in fact, well, I don't want to talk out of school, but basically I've walked by a lot of buildings that we've done in the middle of January, and, the windows are open because the teacher just wants to open a window. But then there's other schools that say they want to open a window because they want to smell the fresh, the spring air and things like that, or the fall air. And sometimes it's a psychological thing too. So that's the balance. I mean, that's the balance in these programs. So if you look at the U.S. Green Building Council and the New Buildings Institute, they will say it's all about energy when it comes to energy. And so if you have fixed windows and you're able to control your environment, then you're using the least amount of energy. But the Well Building Institute would say, open the windows, because it's a psychological thing and people want to be able to open windows. So, like I said, some schools make the decision. We've got 2 or 3 buildings now that they're fixed windows. And I'm talking about libraries and schools that are fixed windows. We have some others who, they're all fixed except for one window. You know, the funny thing today is you can't open a window like you can here. I don't know if you've put limits on your windows here. But windows today only open 4 inches. You know, so you're just getting this little amount of air that comes through to begin with. When they're used to some old buildings that don't have limits, they just throw the window wide open. And, you know, you just, because of fall protections these days, you can't do that anymore. So, you know, it's a trade-off. And by the way, the fixed windows are a lot less money than the operable windows.